Es un privilegio poderles presentar al profesor distinguido Michael Jordan, Universidad de California en Berkeley. Tiene nombramientos en 2 departamentos, tanto en el de Estadística como el de Ingeniería Eléctrica y Ciencias de la Computación. Sus áreas son amplias, resumo que se describe a sí mismo como estadística teórica y aplicada, machine learning, bioinformática, optimización y datos masivos. Y sobre este último tema es que nos va a hablar hoy con la conferencia on Computational and Statistical Interface and Big Data. Muchas gracias por estar aquí el día de hoy.
Gracias. Okay. Es la primera vez que vengo acá en este lugar tan bonito, magnífico. Gracias a Andrés y Víctor que me invitaron. Podría hacer en español, pero no. La próxima vez cuando regreso, creo que hay muchas palabras técnicas que no conozco. Entonces, hago en inglés esa vez. Entonces empezamos. Puedo contestar en español si quieren. Okay. So I'll be speaking about datos masivos. Por ejemplo, una palabra técnica que yo no sabía. Datos masivos. Big data. So for me, big data is a real mathematical problem. It's often viewed as a problem of computer science and building databases and transport and an informatics problem. And it is, but also it's a mathematical conceptual problem that involves bringing probability statistics ideas and thinking together with computer thinking. So computer thinking is about algorithms and runtime and guarantees about runtime. How long will it take? How much resources do you need to achieve a certain level of performance? But the algorithms that have been studied have never been really statistical. There's never been an inference problem that one attempts to solve. So the conceptual problem is to make statements that are guarantees about algorithms and runtime in the context of a risk function, in the context of inference problems. So for some computer scientists that have really never done this, and also statisticians, we have wonderful theories about how risk changes as a function of the amount of data and various constraints, but we never have talked about runtime. How long will it take? And that's really critical in many modern applications. People have to make decisions on a computer in milliseconds and microseconds to do, say, search and financial applications and so on. And in many applications, minutes to hours are kind of the runtime that one desires. And if you had small data sets, that was never a problem. And computers got faster and faster, and there was no problems. But now with data sets in the terabyte and petabyte range, naive procedures will take months or years, and it's hopeless. So, if people turn to us statisticians and say, can you give me any guarantee about runtime? And you say, no, I can't make no guarantees. Then they'll turn to other people. Okay? So we have to face this problem. It's really key. So anyway, let me acknowledge collaborators here. John Lucci and Martin Wainwright have been working with me on these problems for several years at Berkeley. So let's just briefly say something about these challenges. The main one I'm going to focus on for part of the talk is just scale. We have really data sets that are exabyte scale, petabyte scale, and so on. And we still want to do inference of some kind on these data sets. We also have heterogeneity. We have types of data which have changed very much. So in a classical statistics setting, we all learned about matrices, and that was the main kind of data. And now data arrive in the form of strings, like in the DNA setting, proteins. They are in the form of networks, graphs, and blends of this with matrices and classical spatial temporal data. So we have to be prepared to talk about these kinds of data sets. Then we really, as I've emphasized already, have to be focusing on computational issues. And it's not just a matter of making our current procedures faster. It's a matter of giving theoretical guarantees about how fast they're going to be and having trade-offs like a real good engineer. If you want to pay more, you can have this amount of speed. If you need this much more data to get a certain risk function or a certain power, it'll trade off against time in a certain way. That's the kind of trade-offs we need to be able to discuss theoretically. I'll also talk in this talk about interaction with participants. And the main thing I'll focus on as an example is privacy. So if you're going to have lots of data that come from lots of sources and lots of people, many of those people will care about how you use the data, and they'll worry about their own personal privacy or the privacy of others. And so you can't just give that problem away to lawyers to make decisions. No, you cannot use the data, or yes, you can under very strong conditions. You want to have a trade-off. How much utility or risk do I achieve under a certain level of privacy? If you're going to make a major medical discovery based on my medical data, I may be willing to do that. But if you're going to use it for advertising, I'm not willing to do that. And so I want to be able to have that explicit as a mathematical equation. How do I trade off privacy against risk? All right, and we don't know how to do that. That's currently an open problem. So our problem is going to treat, we're statisticians, and so we're going to be talking about inference and specifically minimax risk. And we're going to treat these kind of things as constraints operating on minimax risk. Okay, so we're not going to have to develop a brand new mathematical framework. We're going to go back to the 30s and 40s, but we're going to elaborate it. Okay, so let me just say a little bit about the minimax framework. I'm sure all of you know in a place like this. Starting in the 30s, Wald and others developed decision theory. And the main focus over all the years since then has been how does risk scale with the sample size? We want to now have other dimensions of the space. How does it scale with privacy? How does it scale with computation? How does it scale with parallel processing? And have explicit equations just like we had for how does risk scale with sample size. So just to remind you what risk is, we have a loss function. There's some probability distribution. There's a function on the probability that we like to estimate. We measure a loss based on our estimator, and we take the expectation to turn the loss into a risk function. And that's all vocabulary. If I were doing my talk in Spanish, I would have some trouble with, so that's why I'm doing it in English. And minimax is just one way to start to evaluate procedures over the space of all possible estimators and all possible procedures. So it takes a supremum over all distributions and defines that as the worst case risk, and we'd like to then minimize the worst case risk. So it's not the only way to talk about evaluating risks across families of estimators, but it's one that's been very useful over many, many years, and that's what we're going to continue to use in this talk. So just to remind you of some of the classical results that came out of the Wald, Lecomte, Hayek, notions of logical asymptotic normality, notions of optimal confidence intervals and confidence ellipsoids came out of this. So optimality was a key achievement. And then in non-parametrics, achieving rates that depended on dimension and various smoothness parameters. This has been a great, important part of statistics to do, and it was based on the minimax framework. Then lastly, not least, the last decade has seen all this work on high-dimensional statistics, and it's been fundamentally based on minimax. Okay, so we're going to build on minimax, and just to remind you now, we'll just elaborate our notation a little bit. We have the loss based on an estimator and based on the probability distribution. We take the supremum, and we want to take the minimum over that. That's the minimax risk. What we're going to be doing in this talk is to do one change. So instead of taking the infimum over all possible procedures, we'll take the infimum over a constrained set where the constraints are going to arrive from privacy, from computation, and from this and the other things I was talking about. So that's what we're going to do. We're going to see if we can make mathematics out of that constrained optimization problem. So here's the kind of constraints I'll talk about in my hour today: privacy, communication, and computation. And I might add that when we say computation, you would hope that that would be computer science, that we'd open up a book on complexity theory, and that's the tools we would use. And actually, that's not the case. It's really been optimization theory that has given us the theoretical tools to make statements about computation. So some of the information-based complexity and lower oracle bounds from optimization theory turn out to be very useful in statistics. And someday, perhaps, complexity theory will help as well, but it's really been optimization. So let's talk about part one of my talk will be on private inference. So I think this is all relatively well known or appreciated, that we often have privacy concerns when we reveal personal data. On the other hand, we have benefits that we would like to be able to realize, and we'd like to have a trade-off between benefit and privacy. So we have to quantify privacy in some mathematical way, and then we have to use utilities and risks to talk about benefits. So we're going to develop a model privacy here that's going to be a stringent one. It's called local privacy. I might add there is a whole field called differential privacy, what we'll be talking about, and that word local privacy comes from them. So local privacy, here's the picture. We have data x1 through xn. We're going to put the data through a channel, And we're going to assume that the data is never revealed to anyone, including the statistician. So that each person will put their data through a channel, which will distort the data, turn X into Z, and then the statistician here gets to see only the Z's and doesn't get to see the X's. Another model of privacy, which is often used, is that everyone reveals their data X to the statistician, who then changes the data in various ways and releases statistics based on the data. But the statistician has to be trusted in that situation. And so we're going to study a more stringent notion where you don't trust the statistician, and the statistician might be, Facebook or Google, so there's some good reasons maybe not to trust that statistician. So anyway, the notations, we're going to have a distribution Q, which will turn X into Z. We'll call that the channel. So we're going to use information theoretic kind of thinking, and that language comes from information theory. All right, so we have individuals with private data. We'll assume IID draws just to do some math. And we'll have an estimator, which is going to be based on Z's instead of X's. Okay. We're also, I might mention, our framework allows what's called interactivity, that the process of collecting the data and revealing it, in that process, the Z values can depend on other Z values. Okay, when I define Z2, it can depend on the value not only of X2, but of Z1 and so on. That adds some mathematical complexity, but it's a realistic constraint. Okay, so what definition of privacy are we going to use? We need some math here, all right? And so there is one that exists in the literature. It's not been used for statistical inference very much. It's been used for database theory, really. But we found it useful and have borrowed it. So it's called differential privacy. So here's our channel, right? Condition on either X or X prime, which are two different points in the sample space. We're going to take the supremum over X and X prime. And we're going to then also focus on an event S, and we're going to take the supremum over X. So it's a very much of a worst case kind of framework. So we want the channel distribution for any event S to differ by a small amount when you change from X to X prime. So if X includes my data personally, and a lot of other people's, X prime includes not my data. I've taken my data out. Then the likelihood ratio for any event S doesn't change very much when I'm in or out of the data set. So you can't build a hypothesis for testing framework that tests whether I'm in the data or not very easily if you have this constraint. All right, so that's kind of the intuition. What's beautiful about this really is that it's been analyzed on all kinds of attack models. Data is not arising randomly, but people are trying to attack and use other data to bring in and fuse it with the data given and try to figure out who's in the database and uncover things. So this is resistant to these kind of attacks. So it's been analyzed by theoretical computer scientists, and it's turned out to be pretty robust to various forms of attack. Just kind of a picture here, just graphically, it's kind of a worst case framework that the ratio between two likelihoods is kind of bounded uniformly. There is Larry Wasserman and Zhao have a paper relating this to name Pearson testing. There is a testing interpretation of this constraint. Okay, so here's, going back to minimax risk, here's just our minimax, classical minimax. And so what's going to change now is that we're going to take an infimum, and we're going to have it's going to be one of our constraint situations. And the way we implement the constraint is that the channel must be a channel which satisfies differential privacy at leva alpha. Right? If alpha is turned to be very large, I don't want much privacy. I'm allowing the distribution to change a lot between X and X prime. I'm not trying to be private. If I turn alpha down, I'm insisting on privacy. The distribution can't change between X and X prime. Okay? So we will then have a knob to turn to change the level of privacy, and we will try to find the minimax risk subject to that level of privacy. Okay, so that's our formulation. So now can we actually get some equations, some relationships mathematically on this? And the answer is yes, we can. Just before I show you some theorem, let's just give you an example of this. So let's suppose that we have a situation where we're looking at data from people admitted to hospitals, and they've been admitted for substance abuse. So they might have been using alcohol, cocaine, heroin, or something. And you'd like to estimate that actually, here are the true population proportions. You'd like to estimate those proportions. 0.45 times alcohol, 0.32 cocaine, and so on. Right? But you don't expect that people are going to be willing to give you IID data, and you just take the ratios and get your proportions. They're going to want to not reveal that kind of data. All right, so what we're going to do is take a particular example. Here we're going to look at distributions that have finite support, compact support. We're going to look at the L-infinity norm. In that situation, there's a classical minimax rate, which goes as log of the dimension, the number of entries in that vector, divided by square root of n. Okay, so that's a classical one. It's achieved by the sample mean, so it's kind of nothing really interesting going on there. So if we now impose a privacy constraint, what happens is that this changes, that the n, square root of n now goes to square root of n alpha squared. And we find this in sort of all of our examples, that the classical sample size just changes by multiplying by the square of the privacy parameter. Right? Moreover, the d that was up there before, or sort of log d that was up there before, is changed to be d log d. Okay? That also happens in many of our examples. All right? So kind of a summary of the effect of privacy on minimax rates is that it goes from n to n alpha squared over d. This part of it is pretty good. That's pretty favorable. Alpha is often not so, this change in rate of privacy is not so bad. And it just means that to get a certain level of risk, you have to collect more data, and not too much more data. Okay? That's not so good, though. So in high-dimensional problems, this differential privacy is problematic. It's going to be often too conservative and require you to collect too much data. Let's look at it. So now we have a framework, and there's a theorem behind this. I'll tell you a little bit about how this is proved. Basically, it uses things like Lacombe and Fano inequalities, kind of classical minimax lower bounds, and it sort of carries them through in the setting of this privacy constraint. That's what it does. But now that we have this, we can start to ask questions about, are there optimal mechanisms? So we can calculate this kind of bound, and we can see, are there mechanisms that achieve that bound? Okay, so let's look at that in a very simple situation. Suppose that we report binary data. I used alcohol, I didn't use cocaine, and so on. A mechanism you might think of is to simply change the channel. Would be you take the original data and you add noise to it to give you Z, and the noise might be heavy-tailed, or something known as the Laplace mechanism, which just means you add Laplace noise to X. And in other situations, some situations, that turns out to be an optimal procedure. It's been analyzed in the literature. In this case, it turns out that it's not optimal. It's suboptimal. In fact, could be in high dimensions quite suboptimal. All right. So is there a different mechanism which is actually optimal? And there is. And so here it comes. What you do is you take a vector drawn uniformly in 0, 1 to the d. So there's an example. You take also 1 minus that vector over here. Okay? So you did that randomly, uniformly. All right, and now with probability, which depends on this privacy parameter, with this probability, you pick the closer of v or v minus v to x. Okay, so I hold my data, I sample v or 1 minus v uniformly, and whichever is closer to x, I'm going to give that to you, but I'm going to do that with some probability. All right? And with 1 minus that probability, I'll choose the one that's farther from my x. And so you get to see, as a statistician, v or 1 minus v. And so it's related to x. I've given you some signal, but I've controlled that signal. And this turns out to be the optimal mechanism. Okay? So we have a proof of that. It achieves that lower bound. And in fact, it can be quite substantially better than adding Laplace noise. So here's just some real data from the Drug Abuse Warning Network as a function of the sample size up to 60,000. This is the risk of the additive Laplace mechanism, and this is the risk of the optimal mechanism. So about an order of magnitude difference in risk. Okay, to give you a little bit of a flavor of how this is actually proved, let's make a definition. We have a marginal distribution. There's the data-generated distribution here. There's the channel here. And so the statistician is working with the marginal distribution, M, based on the data Z. And so the question is going to be, if you had two distributions which are far apart and leading to good risk, once they've gone through the channel, they've been contracted a little bit. How much do they contract? That's kind of the mathematical problem. And so we prove what we would call a data processing inequality, which says that the Kolbeck-Leibler divergence between one marginal distribution and the other marginal distribution. So it would, just briefly, when you do lower bounds for minimax risk, you turn the estimation problem into a hypothesis testing problem. So you're looking at the difference between two distributions. Okay, in the Lacombe case, they're really just literally two distributions. And in the more general cases, they're on a grid of some kind. All right, so you look at the Kullback-Leibler divergence between NM1 and NM2, and this symmetrizes it. And we could show that that's upper bounded by something that depends on the privacy parameter. And then we have a total variation distance between the original data generating distributions. Okay, this is what you use in the Fano or Lecomte theory, and it's been altered by this parameter. So we would call this a contraction or a data processing inequality. And this thing, if you just expand it, is, goes n times this goes as n alpha squared. So that's kind of where the n alpha squared is coming from. And another picture of this, if you plug in actually now n alpha squared, it's not just repeating the same thing as before, is basically that two hypotheses which are far apart have gotten contracted a little bit by Q, and this thing quantifies that contraction. And so just to sort of, the technique, as I just already mentioned, is a classical one. We reduce estimation to testing, and we get lower bounds using information theoretic techniques. And Kullback-Leibler divergence arises because of using that framework. So I just gave you one example, but we've applied this to a whole bunch of other examples and have 2 or 3 papers on this at this point. Most of them having the flavor of privacy hurts you by a factor of alpha squared and divided by dimensionality. So here's the kind of generic result. Okay, so that's all I wanted to say about privacy. I guess the last thing to emphasize again is that it's not just a framework for analysis, it also gives you some tools that tells you how to design optimal procedures, and they can be interesting. So part 2 of the talk is going to be about communication. This will be a little bit shorter. So our problem is going to be distributed storage or parallelism. We have huge data sets, petabytes. We can't actually transport the data to be at one central site. We also just might have, for administrative reasons, that data have been separated out. And also privacy, again, plays a role here. I mean, I want to allow my data to be transported to some central site. All right, so we're now going to have a different diagram. It looks the same, but it's different. These are now distributed data at different sites. And now what we're going to do is try to transform that data by a channel again, not for privacy reasons, but because we want low bandwidth. So we want the bit rate from here to be small. Okay, we can't transmit exabytes or petabytes of data. It'll take days. If we want fast data transport to get a fast decision, we have to quantify the bit rate as a constraint on our estimator. Okay, we can't allow arbitrary bit rates. Okay, so the sample, again, size here is X, and we're going to talk about sending messages to a fusion center where the statistician is living, and there's a limited bandwidth on those channels. So we want to trade off between communication now and statistical utility or risk. Okay, so again, we're going to do minimax. We have the same situation before, basically the same notation. Here's the minimax risk. And we're just simply going to add to this an infimum now over constrained procedures, which have a B-bounded communication. So the amount of bits that are going to be sent is limited to be at most B bits. Okay, so Z is B bits because that channel there is limited. Right? So we want the best protocol that's communication constrained. So here's another little example just to get us started. Let's suppose we simply want to do estimation in a normal location family. The mean lives in a compact set, and we get IID data from that. We want to estimate that. And so here's the elementary calculation. The minimax rate is just going to be n, the number of data points per machine times the number of machines. So 1 over the total amount of data, if you will. Dimension appears up here, and then the signal to noise ratio. And if we now impose the new constraint that we have channel capacity, what happened to this risk? Well, this factor stayed there, and we get a new factor which goes as 1 over the bit rate. Okay, so again, just to give you a little idea how these kind of things are proved, you again try to formulate this as a hypothesis testing problem. So underneath the data, you assume there was a set of hypotheses V, and you're trying to ask about information going from V out to Z, and then beyond to the statistician. So again, you set up a ratio of the hypothesis, situation where I have one hypothesis versus a different hypothesis for some event, and then take the worst case event, and you try to make that difference be small. And we again prove a data processing inequality that says the mutual information between V and Z here is going to be related to the mutual information between X and Z, and we pay a factor of alpha if we constrain the bit rate. Okay, alpha here is this value. And then a theorem in the general theorem in D dimensions for mean estimation and regression turns out and in fact all asymptotically linear problems, is that you need at least B to meet the dimensionality of the problem number of bits. So if your channel has less bits than that today, you can't solve the problem. You can't achieve bounded risk. So anyway, given that theorem, we are also then able to show that in a situation where B is bigger than or equal to D, it turns out that there's an asymptotic efficiency result that if you average your local solutions, then that's going to be asymptotically efficient. So let's see. I think that was the last slide I wanted to show on that. So that was meant to be brief. And then the last part of my talk, I do have some time left. Can I get someone to help me change to the second set of slides? Okay, so part 3, joint work with another colleague, Venkat Chandrasekaran at Caltech. So this is now the computation part of the talk. This will be a little bit longer. So here we want to try to actually bring statistics together with computation, as I was saying earlier. How can we get a trade-off between runtime and risk, or trade-off between runtime and amount of data? And the tool we're going to use to do this comes in fact from optimization. It's going to be the tool of contextualization. So just to set up this part of the talk, this I think is an interesting conceptual point, which is that from a computer science point of view, more data necessarily means more computation. And the computer science problem is how to quantify that. So if you have an algorithm that does sorting, and you give, and it has n points in it, they would quantify the amount of time it requires. A lower bound on sorting is n log n. N is the number of points to do a sorting. And then you give me some other problem, they'll quantify with a lower bound the amount of time it takes for any algorithm to solve that problem. And these things are always something like n log n or n cubed or n squared or something like that. And maybe in some nice situations they're n. Okay? But they're always growing in n. All right? So that's for classical computer science problems like sorting or building trees or something like that. But statistics problems are different. So if statistics problems, n is the number of data points, maybe. And n is something I'd like to have be big. I'm a statistician. That gives me power. That gives me inferential strength. If you give me more data, somehow each data point has got the amount of data, the complexity of the problem should somehow not necessarily increase. It should somehow maybe even decrease. So one way to think about that is that as n gets large, we can do asymptotics, and the asymptotic expansion needs fewer terms to be accurate. Okay, that's a fact of probability theory in statistics. So if I were using asymptotic expansions as some kind of a tool for computation, as I get more and more data, I would do less work because I would need less terms in my asymptotic expansion. Okay? That's natural from a probability statistics point of view and very unusual from a computer science point of view. When you think about it, I mean, to make it really patently clear, I mean, if I have huge amounts of data and I have nice assumptions, then I can just use the central limit theorem or a lot of large numbers and get the answer without any computation at all. So anyway, that's maybe a ridiculous version of the story, but there's somehow the idea that you should do less work when you have more data seems natural. It seems new that we should be working on this, all right? So let's see if we can do that in some, again, mathematically sound way. So the way we're going to try to do that is we're going to have a notion of controlled algorithmic weakening. That you may have a very expensive algorithm that works really, really well. And in a statistical setting, what that's going to mean is that it gives you, it's maybe optimal. It gives you low risk. All right? But it's maybe computationally very different, n cubed or something. If you have a very small amount of data, you're happy. You've got the optimal procedure and it works in a fast amount of time. Right? But as the amount of data gets larger and larger and larger now, n cubed becomes bad and eventually becomes hopeless. All right? You can't use it. All right? So maybe you're lucky enough that you have a different algorithm sitting ready to go, which is n squared or n log n, or maybe all the way down to n. And it's going to be a cheaper algorithm probably. It'll be less good in terms of risk. It won't be optimal anymore. But it's so much faster that as the amount of data arrives, the strength of the data will make the risk actually still go down with a cheaper algorithm. Okay? Because you can process more data in a certain amount of time. Therefore, you need less of an optimal algorithm. And again, it's not very common for statistics thinking. We're used to what's the optimal algorithm, and then you try to make it as fast as possible. Right? But if I impose an hour time limit on you, you must process my data in an hour. And I give you a certain amount of data, and then I give you more data. You should be only happier. You shouldn't say, oh my God, I don't know what to do now. But that's what we do. We do say, oh my God, we don't know what to do. Right? And if I give you huge amounts of data, you should be super happy. Right? And so if we didn't impose the 1 hour or the 5 second or the 2 millisecond constraint, you would be happier. You with more data. Right? But with the time constraint, you're not. All right? And so a lot of our statistical inference procedures have a very unclear relationship to runtime. Okay? Very unclear. In particular, all the MCMC procedures have an unknown, completely unknown relationship to runtime. In theory, there's a second eigenvalue that no one can ever compute. So, anyway, so let's try to do this in some simple setting. I don't think we're going to solve this whole problem. It's a kind of big open problem for the next several decades, I believe. But let's try to make some progress on it. All right, so let's try to be clear on what we're trying to talk about here. So we're going to put together a number of samples, which is a classical statistical thing, with runtime, a classical computer science thing. We're going to have them in the same plot, and there'll be a third axis, which is the risk. Okay, that will bind the two together to make them talk to each other. All right? And the way we turned out to make some progress on this problem was to actually fix the risk. All right, so there is actually a surface of some kind in 3 dimensions. We're going to fix the risk at some value, maybe 0.05 if it's a kind of an error. And then that'll induce a curve between the, by slicing the surface, we'll get a curve relating the runtime and number of samples. All right, so this is not completely unfamiliar. In classical estimation theory, the minimax things I've been talking about, you would talk about the minimal number of samples you need to achieve some level, fixed level of risk, irrespective of the procedure. Therefore, obviously, irrespective of runtime. You don't need the computer scientists because it's for any procedure. Okay, and we know where that curve lies. It is the minimax risk. I showed you some examples earlier, and we know procedures that achieve it for lots of situations. Right, but those procedures, lie at various places on the runtime curve, and often we don't know where they lie on the runtime curve. We just know they're up against that line. Similarly, in computer science, there is a notion of lower bounds on complexity in complexity theory. You would like to be able to say, what's the minimal runtime I need to solve some problem, irrespective of the size of the problem. Right? And there are attempts at such results. There are many fewer than in statistics. It's a harder thing in some sense. It depends very much on the computational model and so on. So there's big gaps. There's some kind of known lower bounds, but the upper bounds are much bigger, and no one knows how to close the gap. So it's still open where this line lies in lots of situations. Anyway, we're not so much interested in those lines. We're interested in trade-off curves. So we're interested in being able to say what's a relationship between runtime and number of samples, and what are specific procedures that lie along that curve, so that we can allow a user to move up and down the runtime number of samples curve as they get more data or as they have more of a budget on their runtime. Okay. So our problem is to denoise a signal. So X star is our truth, the signal we'd like to infer, and X star will have additive noise at some noise level. Okay. Let's assume the noise is Gaussian, so we can do some mathematics. So we have an additive Gaussian noise. And we get IID samples, and we'd like to, from these samples, recover X star. Okay, so the classical, simplest problem in statistics. Regression would have a design matrix here, making life more complicated, and we don't have that design matrix in the denoising problem. So we have IID data, I assumed IID. So let's take a sufficient statistic by taking the sample mean, adding up the data. All right, and now let's turn this problem into an M estimator, or an optimization problem. And so what are we going to do? We're going to assume that we're going to build an estimator, X hat, based on okay, so let me go back here. Script S is the only thing complicated on this slide. So script S could be a complicated set of some kind. Maybe it's discrete, maybe it's non-convex. That's the only complication, so we have to cope with that. So we're going to optimize, in this case, an L2 loss. We're going to assume L2 loss so we get some geometry helping us out. The estimator will range over X in the set S, and we'll take the minimum contrast, or minimum the minimum L2 difference between that and the data. Okay, so we would call that our estimator based on S. Now, there's 2 reasons we probably don't want to use that estimator. The first is statistical, which is that this is a complicated set that we probably will overfit if I give ourselves the full freedom of that set. We probably want to have some kind of a regularization to obtain a regularized version of S. The other reason is computational, which is that S is often going to be discrete or non-convex, and therefore this problem will be intractable. It probably will be NP harder or worse. So for both those reasons, we will probably want to relax to a simpler problem, where S is relaxed to a set C that contains S. All right. So So this will, if S is not convex, we will often want to make this thing convex, and that will be called a convex relaxation. And so that idea of relaxing to a convex outer bound is widely used in applied mathematics and optimization, and we're borrowing that idea. Okay, so now we define a new estimator, which is given by optimizing over the set C. This is going to be convex typically, and so this problem has some hope of being, it's probably going to be at least polynomial time and maybe efficient. All right, so just to get a picture of that, here's our original set might be even discrete, given it's an integer program, which was probably going to be intractable. We would relax to the convex whole in this case. And now to set up a statistical, so the computational side of this story is actually already kind of completely known. There's a lot of convex relaxations, and for various problems it's known exactly how the runtime changes as you relax to the set C. And then you can relax to another set a little bit bigger, and so on, and get a sequence, a hierarchy of these relaxations. And it's known exactly how the runtime varies, but lower and upper bounds on the runtime for these things. So that's the computational theory. Really, it's out of optimization theory that we're going to be borrowing from. And that theory has a lot to do with geometry. So often you will go from, say, a semi-definite program to a second-order cone problem to a linear program, which is your sequence of relaxations. And your runtime comes out analyzing the geometric consequences of those different kinds of relaxations. So we're going to try to now develop a statistical parallel to the computational story. And the statistical parallel surely has to use the geometry also. That's good. So actually it's geometry which is going to go between computation and statistics. It's the link. So to get some geometry started, let's define a little bit of a notion for convex geometry. Here's a point x star, which might be on the boundary or might be inside of C. We'll define the cone just to be all those directions that depart from x star and stay inside the set C locally. Okay, so that'll be defined for this object, grounded its x star with reference to the set C. All right, so now we have a theorem, which is a statistical theorem, all right, which is the following. We're able to show that the risk, that's a risk, again, it's an expectation of a loss, where we're using the LT loss. So again, x star is the truth, we have our estimator, we take a difference, and then we take an expectation where the randomness is in the x hat. So we're able to show that that risk is upper bounded by a kind of classical sigmoid noise formula, the noise ratio divided by the number of data points, then times this expectation here. This expectation is purely geometric and it's geometry and probability. There's no data here, and so there's no statistics. This is just geometry. So what we're doing is we're taking the inner product between a direction delta, which lies in the cone T, right, and Z, which is taken from, it's noisy, from the Gaussian distribution, and that's what the expectation refers to. It refers to Z. Okay? So we square that, and then take a supremum over all directions delta. Okay? So that's not unfamiliar. That in empirical process theory, this would be called a Gaussian, something like this. You can have the square right there, which would be called a Gaussian width, or Gaussian complexity. All right? It turns out the square is important for us and gets us tighter bounds. So we call this a Gaussian squared complexity. All right? And the point is going to be that we're actually able to calculate that in certain geometries. So some of the examples, we get a number. That whole expectation is just some number. Okay? It'll be dimension dependent, which is good. You want to get the dimension in there. But it'll be just a number. All right? Now, the key is going to be that we're going to be able to use this tool now to look at C as it varies from a small set to a bigger set. We're looking at these sequence of relaxations. So notice if I were to compare this for two values of C, let's take C to be small versus big. All right? So the cone is going from small to big. For the small cone, the number of directions available to us, there we go. So this delta is ranging over this cone. If the cone is small, there's only a few set of directions here. And the supremum, we're taking the supremum, is limited. Okay? If I take a bigger cone here, then I'm taking the supremum over a bigger set, and the biggest inner product I can achieve gets bigger. All right? So this quantity can only grow, this whole expectation can only grow as the set C grows. And that's good, that's relating, it says the risk is growing, more likely to grow as I get a bigger set. So the computation as I get a bigger relaxation goes down, I get a cheaper geometric optimization problem, and the risk goes up So we're starting to get this trade-off we want, where as I relax, computation goes down, risk goes up. And I can go in the other direction. All right, so in fact now, as I mentioned earlier, what we're going to do is to set the risk to a fixed value. So without loss of generality, let's set this risk to 1, okay, without some constant. And then rearrange that equation. We say that if you want to achieve a risk of at least 1, or most 1, then the number of data points needs to be greater than the signal, the noise, times its number. So if I can compute this number, I can tell you how many data points you need to guarantee a risk of at most 1. All right, so if I have more data, which is going to be possibly good, all right, then I can use a larger set C and achieve a risk of at most 1. And now the computational person is happy because a larger C means a cheaper algorithm and they can do it in less time. All right, so there's our connection. So let's now make this a little more explicit about these nested sets. So if I started with S here, and I relax it to a set C, I can also consider further relaxations that are outside, outer relaxations, right? And therefore my cones will only grow, and my risk will only grow. So what relaxations do we use? Well, again, as I mentioned, we start borrowing this from the existing computational literature, really the combinatorics literature. So various relaxations exist. They're known as polyhedral, semi-definite, hyperbolic, and so on, just to reflect the different geometries and the various names associated with these things. The literature tells us how to order these things, not only geometrically, but also by computational complexity. All right, so let's do some examples, and this will be the last part of my talk. So let's now do some inference on some combinatorial problems. So kind of an unusual thing for statisticians maybe, but I think very, again, harkening back to the beginning of my talk, the new data sets we're looking at need combinatorial data and structures. So here's one. Let's let S, the signal set, consist of a set of cut matrices. Okay, these are just matrices which are gotten by the rank 1 matrices, outer products between Rademacher vectors. Okay, A is just a vector of plus and minus 1s. I take an outer product of that and I call that a cut matrix. So think of a graph in which some of the nodes are 1 and some of the other nodes are minus 1. And the cut is the boundary between the 1s and the minus 1s. And I might, as a statistician, want to infer a cut matrix given some noisy data. All right? So we would have to solve it out. We have to have an algorithm to find the best cut matrices under given certain amount of data. And so we would look, if we try to optimize that over that set S, the L2 norm, that is a known interactive NP-hard problem. Can't do that. Okay? The first relaxation is to go to the convex hull of S. That has a name. It's called the cut polytope. And there algorithms exist which are super polynomial in P. Now what is P? This is a P-dimensional, it's a square root P by square root P matrix. So there are P entries. It's the number of dimensions in a problem we're trying to infer. So that's the P. So there's a known algorithm which runs in super polynomial in the number of entries in these matrices. Now there's another relaxation, which is a little bigger, called the elliptope, which has a known algorithm that runs in time P to the 1.75. And then a further relaxation to the nuclear norm ball, yet bigger, runs in this amount of time. Okay? Now the computer science literature, these are just borrowed from the computer science literature. Typically these algorithms higher up in the hierarchy are preferred. They have better approximation ratio. Approximation ratio is a worst case geometric quantity over the entire object. It has nothing to do with statistics. All right? So now if we look at the statistical theory, this is this new column over here, that comes from our theory. So here, if we now calculate this Gaussian squared complexity, to achieve a risk of at most 1, we need to have n equal to this or greater than or equal to this value. So for the cut polytope, it needs to be square root of p times a constant. Also for the elliptope, it's square root of p times a constant. And also for the nuclear norm ball. It turns out that it doesn't vary in dimension at all, it just varies in the constant. So the constant has to get worse, and indeed it does, but it's just the constant. And so from a statistical point of view, you much prefer algorithms down here. These much cheaper algorithms give you essentially the same risk. And so you're going to be able to process much more data, achieving the same risk with the cheaper algorithms. So approximation ratio is maybe useful for other problems of computer science, but for statistical problems, it's not the right measure at all. It's giving you the wrong message. It tells you should be up in these algorithms And statistically, you should be down with these kind of cheap relaxations. All right, does that hold true for other problems? So here's another one where we have the signal set being all perfect matchings in a complete graph. Again, this has been studied in computer science literature. There's a convex hull result known for it, where there's an algorithm running in time p to the third, and there's a relaxation with a hypersimplex running in p to the 1.5. Again, it turns out statistically, the complexity, the statistical efficiency is the same up to a constant. And so you again would prefer the cheaper relaxation when you're trying to infer matchings in a complete graph. Here's the sparse PCA problem. We're trying to, let's ask the adjacency matrices of graphs with only a clique on square root many nodes. So it's called a planted clique. You have a clique on a small subset of the nodes, and you like to find that in a community detection problem. And again, it's going to analyze computationally. There are algorithms known which run in super poly and p to 1.5. Here, statistically, actually, there's a little more of an interesting difference. Here is p to the 1/4 and p to the 1/2. Okay, so especially for large p, you might prefer the higher this algorithm for longer as it gets bigger until you switch over to this algorithm. Okay, and then this is my last problem. This is my favorite one. So we're going to look at the situation where we're trying to estimate covariance matrices in high dimensions. This is a problem many people have been working on. And there are these class of estimators, they're known as banding estimators. So in high dimensions, you have a big covariance matrix. The number of entries is huge, and you have not enough data to estimate all those entries. So you maybe set almost all of them to 0, and just for a band around the diagonals, you allow those things to be non-zero. Now you can only do that estimator if you know the ordering of the variables. If I change the order of the variables, the band will change around. Okay? So in some problems, like time series, I would probably know the order of the variables. It would be the time series. And banding is like an AR model, would make sense. But in biological or other kind of network problems, I have a bunch of proteins that are interacting in some way. I have no idea what the right ordering is. So that's the inference problem. Is given some data, find the right ordering such that a banding estimator makes sense. All right, so we've set that problem up as follows. Let M be some known tridiagonal matrix, and now you have a permutation matrix pi that permutes M, and the signal set is the set of all matrices obtained by ranging over the permutation group for a known tridiagonal matrix. The problem is to infer pi. After you've inferred pi, you've made the order of the variables, now you can do banding, and that will allow you to estimate M. That's not the interesting reference. Okay, so here we go. Again, we have a combinatorial problem, and it turns out the computer scientists have analyzed that. For the convex hull of this set, this permutation orbit, you get a super polynomial time algorithm. For a certain relaxation, you get p to the 1.5. And again, statistically, it's kind of interesting to see that statistical risk doesn't change as I go to the cheaper relaxation, except in the constant. So again, this is probably the relaxation we use for modest-sized problems. Okay, I think that's the last example. I don't think I have much else to say. So we have a paper on this. You can look at it. There's some other examples. It's a fact about all the examples that the cheaper algorithms are preferred statistically. That's kind of a folk theorem that for very large data sets, cheaper algorithms tend to be remarkably effective. It's kind of people often say this. And this is the first theoretical evidence of that. There's some truth of that. Also, the other comment I've already made just make it one more time. Approximation ratios is what's studied in theoretical computer science. We're arguing that as statisticians, we should be studying this object, Gaussian complexity, but we also hope that theoretical computer science will study this too. It's just as interesting as this for different classes of problems, and they will look at their theory differently, I think, if you think about that. I guess I'd also say that that's the first paper that we've done on this topic. It's the first paper where we have a real curve between computation statistics, and it's very limited. It's for denoising, it's for IID data, it's for Gaussians, so many limitations, and it really needs more work. And I hope I'd encourage many of you who make some interest in this emerging area to get involved, because it really is just beginning. There's lots of things that one can do. So that's the third part of the talk, and I don't have a slide concluding the entire talk, but let me just hope that you've captured some of the themes of what we're trying to do. again, we are interested in this big data regime because it's real. Society is really delivering us problems with huge amounts of data, both in science and technology. You see it in both science and technology. And they want to do inferences on this kind of data. They don't want to just store the data and look it up and query it and index it like the classical databases. They want to do inferences. They want to predict from the data who's likely to do what tomorrow, what risk do's, what medical profile people have, how do I do personalized medicine, and so on and so forth. It's all inferences. So we have to control the risk. We have to be statisticians. But we have to be computationally responsible too. We can't just say we have some algorithms that we hope would run on that data, but we know they really won't. That's what we've been doing for too long. So anyway, it's a mathematical problem. It's also people are building systems, and that's great. But they can build systems until the cows come home. I don't know if that metaphor exists in Spanish, but they can build these systems all day long, and there's a good chance those systems will not control risk in any reasonable way. There's a good chance those systems will make all kinds of horrible errors, again, on large data sets with large numbers of inferences. So we have to really engage in this problem. Okay, gracias.
Muchas gracias. Preguntas pueden ser en español, por supuesto.
I like it very much because last year I went to several talks on big data, and people were saying, forget about theory. There is no theory anymore on these big data. So this is really...
I think it's exactly the opposite, as I'm trying to emphasize. In fact, a lot of procedures that, we have a lot of procedures in statistics and machine learning which have good guarantees, that are very nice theories that really do work on small data sets. It's very satisfying. When the computer science will get a hold of those theories, often they will try to do something ad hoc, algorithmically. They'll make it parallel, they'll make it streaming, they'll do all kinds of operations on the basic structure. And now the theory, the guarantees are gone. Right? So if you take a matrix, for example, and you guarantee incoherency, and therefore I have sparse regression guarantees, and you now take pieces of the matrix and do it separately and then aggregate them, a very common heuristic to do to make it scalable, the coherence of the submatrices is now changed, and the guarantees are gone. Right? So do you just live with that? Do you say, well, to make it work, I had to do these ugly things? No, you have a new theoretical problem to solve, which is that if I break up a matrix into many, many pieces, and the coherency goes up, are there operations that still restore the correctness? So I actually think when you start beating up on big data with algorithms, you have brand new theoretical problems.
¿Alguien más? ¿Pregunta?
Sí, pero si estos resultados pues obviamente son correctos, entonces ¿qué tanto aún necesitamos el cómputo distribuido para aplicar este tipo de problemas que son de información gigantesca como terabytes? ¿Aún así necesitamos ese cómputo distribuido?
So we have a project at Berkeley called the AMP Lab, which is exactly about me and working together with a bunch of people who do databases and build distributed systems. And these guys are really, that's what they do for a living. They're very good at it. They're the kind of people who built Google. Behind the scenes, you have tens of thousands of processors serving requests in a very nice computer science way. But they've never thought about statistical issues. So one of the first projects we started on with them, a little more practical, but was just saying, let's get error bars on all of your queries. A classical database, you give it a query, it gives out an answer. I'm a statistician. A query comes out, I want an error bar on the answer. Let's build a database around every answer you get an error bar. And so I said, oh, I know how to do that. The bootstrap will do that. Right? So then the problem became a problem of how do you make the bootstrap work on terabytes of data? And if you think about, the bootstrap, you have to resample the original data with replacement. I can't do that at terabyte scale. It gives me data, many data sets of terabyte scale that I'm sending around. I can't do it. All right? So we came up with a new idea called the bag of little bootstraps, and it's appearing in JRSS later this year, which actually is a really computational new way of thinking about the bootstrap. Kind of surprising. We think the bootstrap is so simple, but it's unscalable. So there, actually, the computer science thinking helped us to kind of realize there's a scalable way to think about distributed bootstrap that allows you to do classical bootstrap inference correctly at scale. So computer science are good at this word scale, and I think that's kind of for us to take very seriously. What does it mean to scale? So I didn't answer exactly your question, but I just So in some sense, one answer, you have to be collaborative, it really is. The problem of having, maybe an institute like this is perfect, mathematicians, computer scientists, and statisticians. You should be getting together and looking at some of the problems that emerge with terabytes of data. You do some classical statistical procedures, what assumptions do I need to make? Random matrix theory, for example, is critical for us to prove some of the theory behind this. There's a paper coming out of Annals of Probability on Stein's method for random matrices, which is this month. That was driven exactly by taking matrices and breaking them up in problems so we could do distributed processing of matrix problems. It turned out that you couldn't prove anything about it in standard ways, and Stein's method allowed you to make some progress. So, connect them up.
Parece que ya no hay más preguntas. As I mentioned, this was a 2013 conference. It's no longer 2013, but I'm sure in eBay
Okay.
will go well.
Thank you. Okay.
Thank you.
Okay. Gracias.